And he suggested to very young Ørsted that between magnetism and electricity there must be certain relation, given the fact that both natural phenomena are notable, are written down by plus and minus signs. So there must be an affinity or some family relationship. And this idea of positive and negative, and in German idealism, was further on paralyzed by the fundamental difference between a male and female being and so. But to come back to Ørsted's crucial experiment, it was not an intended planful experiment, but during a lecture he switched on the voltaic battery before the eyes of his students. And then magnetic iron was in the neighborhood, and then he switched the electric current off again. And when he switched on, and when he switched off, and only then, the magnetic iron showed a little trembling or some movement. As Ritter had suggested to him, electricity can induce magnetism, as we nowadays say. Can be electric energy can be converted into magnetic energy, movement and activity. You have remarked that when this electric current was on, flowed for some minutes, nothing happened. Only this event of switching made the effect, and this was, and so Ørsted, without knowing it at his time, had discovered AC, alternating current, changing current from plus to minus and from minus to plus, and so on. And otherwise, I would have been able to correlate in a symmetrical or anti-symmetrical way two names and not just one. The break came too early in a sense. This Hans Christian Ørsted and Michael Faraday, the famous Englishman, closely hold together as a pair of inventors because the autodidactic inventor Faraday just inverted Ørsted's approach. He was a multi-inventor and a very productive man in many fields. For instance, he discovered the so-called stroboscopic effect, which is elementary to movie perception. But for our purposes, much more important is this electromagnetical discovery. Remember, thanks to Ørsted, we know that moving electricity moves magnets, and now it's just the other way around. Moving magnets induce electricity. We can, thanks to Faraday's experiments, produce electric currents, or to put it more precisely, alternating currents, because the movement is a circular movement normally in an electric generator, something Rolls or Cycles. And so the produced electricity changes from negative pole to the positive pole, and the wheel in itself has a mathematical property to produce not just circles, but trigonometrical functions, and to be more precise, to produce sine waves or cosine waves, which is almost the same thing. But please, take your mind and your heart in both hands and imagine mentally all the time here in these 3 days this wonderful function. Let's take the case of the sine wave. The two maxima are +1 and -1, but on the horizontal axis there is no limit at all. The sine wave is older than God and will stay longer than God's creation, from -infinity to +infinity. That's its property, sorry. And this is AC, alternating current. And the moving magnetic coil breaks down to the very concept of an electrical coil, die Spule, and has a symbol which we don't need. This way in German, and when I understood correctly, Thomas Pynchon this way in America, but I'm not sure. We don't need coils, and we don't use coils anymore today, except in the cases of high frequency reception. Probably in mobile movies, some coils may be implemented on the receiving end. And coils are the inverse or the opposite of capacitors, inductivities, coils. Let's come to all this difficult stuff later on. But strangely enough, the nomenclatura, the naming, the technical language of electronic engineers has looked out Michael Faraday as a name giver of quite another phenomenon, the capacitor, which is measured by the unit named farad, or farad in English probably. And this will be very important for us. Historically, it doesn't make sense, it's just nonsense. He didn't invent the Leiden bottle or something like this, or the modern capacitor. But now we have together all the three fundamental elements of electricity as they were discovered in the 19th century. And I can give you the first working model. We have capacitors, we have currents, alternative or direct, And thing I didn't mention, we have resistors, some elements which make it difficult for currents to flow, or more difficult for currents to flow. And some German white man, in fact, Georg Ohm, formulated in the late 40s of the 9th century the elementary law of electricity, which isn't disrupted or thrown away by electronics and computers and internet. And Ohm's law is the only mathematical formulation are used in these courses. Voltage after volta, short sign U equals current I times resistance, or in Europe we have a mnemonic little device to make it easier to memorize Ohm's law. One of the Swiss cantons is called URE. U equals resistance times current. And in the course of time, units have been defined for these three elementary entities. Voltage is measured in volt. For German ears, it would be a little more complicated to explain. Resistance is measured in ohm, after the inventor of the law. And ohm, and this ohm, this long ohm, O of ohm, is written down omega, because the normal O was already given away for another unit. And current intensity is measured by ampere after a great French scientist shortly after Napoleon's exile. And when I prepared this course, I always look back at my happy childhood in a small village in Saxony. And I thought I must explain everything, or as much as possible, to you by pictures of creeks and small rivers and dams and pools and water mills and so on. And I should reformulate this Ohm's law by the following example: a small creek, little ampere, with high resistance, narrowness, a narrow pipe, let's say, gives a big incline, a big drop, a big voltage. Also, the river is small, the voltage can be big. Sounds at first sight a little bit paradoxical, but this is Ohm's law and the relation between the three units. So far for theory today, and now to media, technology and infrastructure and so on and so on. And urbanists will come to their coast. Wolfgang Schiedelbusch, a German writer on history of science, living partly in Germany, partly in New York City, has written a wonderful book on the introduction of the railway system into Western culture. I'm quite sure this book has been translated into English. Any shows, unhappily, not at great length, the systemic or systematic interrelation between the railroads on the one hand and the electric telegraphy on the other hand. Take a train, take a tunnel, okay, take tracks, take two trains and this tunnel, and all can go wrong. 500 dead. Accident. And so telegraphy is not just a corollary, but a necessity and a precondition of a functioning railroad system. The stations and the trains themselves, the train leaders, must be informed about each other and their position and their time and their situation, their position in time and space. So, before I come to the introduction of electric telegraphy in a less cruel sense than in Barcelona once, a short remark about steam power and railroads. Beyond Schiedelbusch, in fact. After James Watt and his invention of feedback assured steam engines, and after Faraday's invention of electric generators, the question of industrial power and energy was posed in a rather scientific manner. The great Carnot, Lazare Carnot, who made possible Napoleon's victories by organizing the armies and la levée en masse, and his sons exiled in Magdeburg, Germany, because they remained true to republican ideals and the emperor, and had to leave France after the Restoration. Invented is nonsense. Constructed the theory of thermodynamical systems applied to temperature. This is to vapor. This is to steam power. And Ludwig Boltzmann, suicidal Ludwig Boltzmann, 1 century later, closed the theory of the thermodynamics by introducing the concept of entropy in closed systems. We will come back to that. And in case you want to learn a little bit more poetic, you should read the early Pynchon's short story, Entropy. every closed thermodynamic system will end in heat, and indifferentiation form, in other words, in some death. Without any voltage, so to speak, there is no more life and energy, and no event can happen anymore. Okay, back to telegraphy. One five-finger rule: telegraphy, electric telegraphy, and only electric telegraphy differentiates historically between communication and information. Before, and even in the case of optical telegraphy, humans and animals, horses, and technical means, relay stations or so, were already always connected. And now a telegraph cable has nothing to do with humans or animals. And you in America, you see so many telegraph cables, even these days, where all these cables in Europe under Earth long disappeared from our eyes. I skip the scientific origins of electric telegraphy, going back to the greatest German mathematician of the 19th century, Gauss, Carl Friedrich Gauss, and his colleague Weber in Göttingen. I mentioned the English Whetstone, I think it's pronounced, who introduced some digital equipment on the input and output side of telegraphy. You could more easily tape and read. Whetstone, also the inventor of the stereoscope and stereoscopy. And all this happened before the eyes of an American painter on his European trip through Europe. It was Samuel Morse who learned about optical electrical telegraphy and transferred it to Baltimore, I think. And his crucial gift to electrical telegraphy was the introduction of a code, of a code which is still alive and in value. And you all know the Morse code, but no, not all of you probably have understood its properties. Does someone amongst you know the short story Xing a Paragraph, written by Edgar Allan Poe? Some newspaper journalist in this fictive story makes a joke to replace in the printer's case, all E's, all letters E, by the letter X. And then the newspaper simply becomes unreadable. And Poe and Edgar Allan Poe, great crypto analyzer, as you know, and Morse discovered the same, or rediscovered the same statistical phenomenon in languages such as English or German, there are many E's and very few X's. And Morse, but in the usual alphabet, E takes just as much place as does X. Whereas in the Morse code, E is symbolized by one short dot point, and X is made up by at least 5 Morse signs. And this is the first difference between alphabet and Morse code. And the second one is, and so you see that first difference, the Morse code is an optimized alphabet. It's more economic in technical sense. Takes less time to transmit the signal because the Morse operator is just to make that for E and this. And the second property, I forgot. Yeah, it's a binary code. There are only dots and dashes and nothing else. Okay, you can say it's a triadic code, dots and dashes and pauses. Pauses are important for the understanding of Morse messages. And after Morse cables, telegraph cables had been laid on land in the Crimean War, for instance, for military reasons, between St. Petersburg and Sevastopol. And after telegraph cables had finally and painfully been laid out from Shannon, Ireland to Newfoundland or what else in the New World, underwater cables, durable, not catastrophic cables, the world became, for the first time in its history, a global unit. It was not capitalism as such, but technical infrastructure. And naturally enough, from telegraph cables arose new newspapers, new international agencies as Agence Havas or Reuters in London and whatever. United Press, Associated Press in New York, and everybody of you knows the old-fashioned conservative London newspaper, the Telegraph, speaking name. But it proved difficult for New York and the New York Times to cross the River Hudson at the height of New York, and so the cables went from New York first to Richmond, and then at Richmond the river could be crossed, and Richmond became very important for telegraphy, American telegraphy, and Kodak and photography and so on. And that seems to be the reason why in Richmond, upper New York also, upstate New York, in Richmond, 4 crazy young sisters showed up out of nothing and pretended to have heard by night in their dreams knocking spirits. Knocking on their door, on the table, and about 1850. And these knocking spirits became famous nationwide, US-wide, by the agency of the New York Times, which propagated this first mediatic effect, wonder. Not Christian spirits or pagan spirits anymore, but technical spirits showed off as another side of as the backside of technical media, parapsychological media, as an surface effect of technology, let's say. This was just a remark on the Fox sisters. Now let's forget about vapor and steam power and come into the system of the second half of the 19th century, where Germans like Werner Siemens, later Werner von Siemens, electrified the whole industry, alternating current as motor, alternating current that is as driver, alternating current as product of rotating magnetisms. This was the electrification of Middle Europe. And Tania has prepared for you. It's okay, Tania?
Oh, actually, I would move the beamer, but maybe we have to speak. Yeah, someone has to set it up.
Yeah.
And do there was no cable or anything, so.
Let's postpone it.
I think we should better postpone it. So it makes more sense to see things. Or I did without the pictures. That's the other.
Yeah. We had prepared to use some minutes on the topic of the electrification in our city of Berlin, and the electric railways, the subway and the cityway, U-Bahn, S-Bahn, for those who ever saw Berlin with pictures. As it is our sworn aim to make you at home, to recognize your cities by images and pictures as products of technological development, I think we'll postpone it in reason of the pictures. And from Werner von Siemens, the great German industrial whose company is still very alive, I'll come to his son-in-law, Hermann von Helmholtz, one of the greatest and most venerable physicists of the 19th century. And I think this will be the first scientist I present to you in some length. Helmut's father was a high school teacher and inspired by German idealist philosophers at its utmost, Fichte. And son did everything he could to put idealism on this earth, to earth it in a way. And so he was the first to really answer the question or the problem posed by Galvani's experiment. Why did those frogs tremble answer, because our very nerves are electrical conductors. This was proven experimentally by Helmholtz before he got his Nobel title. This made him famous for, before all, his discovery that our nerves are bad conductors, very slow, and that's why car drivers die. It takes them a tenth of a second to react. This was Helmholtz's discovery. 2 meters, the nerves from the eyes to the brain, just some centimeters, and nevertheless, the electricity flows so small, so slow, and in copper cables, it's almost it flows almost at ideal velocity, that is light velocity, that is absolute velocity following Einstein's relativity. And then, after having discovered the electrical nature of our body, Helmholtz went on and wrote 2 standard monographies on our eyes and on our ears. The first connecting our eyes to Newton's light theory and optical arts. And in my eyes, more important is the second monography on our hearing, on systems of music, on Pythagoras and polyphonic harmony, and the mathematical laws behind music, and the first Fourier analysis of musical sound. I'll come back to this hairy issue, difficult to explain. These are books very recommendable even today, and surely translated. And 1 year before his death in 1893, Helmholtz traveled to the World Exposition in Chicago and was given a key lecture by his American colleagues. But after much, at the end of his conference, Helmholtz didn't shake hands with his famous colleagues, his hosts, but went through down the middle floor to the last line in this big audience, and there was a man without a Ph.D. title was sitting there, and Helmholtz shook hands with him. This was Thomas Alva Edison. Because I think Helmholtz had done all for the analysis of music. He had written down musical signals and so on, but only Edison could have the idea, when you can write down musical frequencies, you can reproduce music by phonographs or later on gramophones. And Helmholtz himself had missed this crucial point, and that was the meaning of this shake hands in my eyes. Helmholtz was engaged in the standardization of electricity. That is to say, he was one of the leading men who made up this system of volt and ohm and ampere. You don't know that, and it was very important. I could talk about hours about the fact that this standardization of electrical units was crucial in every thinkable way. You can't see electricity, you can't hear it, but you can die by electroshock, or you can be electrocuted. And so electricity must be made measurable, and in order to be measurable, there must be measured, that is, units, and these units must or should ideally correlate to other decimal units as introduced by the French revolutionaries, in difference to inches and ounces and such medieval stuff in England and America. And so volt and ampere and ohm are immediately translatable into meters, seconds, and grams. It's one of the same standardized system, nowadays called ISO, or International Standard Organization. That was, don't misunderstand please. I didn't say that America and the US Army, in fact, didn't make a contribution to standardization. America, in continuing a French practice, an older French practice, standardized guns, revolvers, and things like this. And from this, and from revolvers and guns, later on, after the Civil War, came typewriters and sewing machines and so on. But remaining inside the domain of science, one important student of Helmholtz was Ferdinand Braun, German writing of the same. We did under Helmholtz's direction a dissertation, Ph.D. thesis on crystals under conditions of electricity. And it was Ferdinand Braun who, I think 1874, discovered a surprising, totally surprising effect. He discovered chemical objects, namely crystals, mathematical and chemical things, which were not just isolators or conductors, but something in between. What we, in the computer community, nowadays call semiconductors. My pronunciation is correct? Yeah. Semiconductors, yeah? Halbleiter. And all transistor technology and chip technology is based on Braun's discovery. That is tomorrow's topic. And Now you see again my idea. Sine wave. This will be the input to one such crystal discovered by Braun. I give you the first electrical diagram. This is electrical input, AC. This is the symbol for input. This is just symbol for wire. This is the crystal, symbolized by a diode. And the output looks like this. You see what has happened? The positive half of the signal has passed through, and the negative half of the signal has been stopped. Doesn't get through. And this is called, since Braun, an equalizator, I think, or a rectifier. Tomorrow we'll bring our lexicon. Early radio reception wouldn't have been possible without this crystal. And when in the Christmas days of 1947, the transistor was invented in the Bell Labs, Braun's discovery finally came to its summit. When Edison was 15, the Civil War raged, and Edison, I think, lived in Chicago, and the newspapers, Chicago newspapers, were not connected to telegraph lines, and so the news of victories and defeats in the war arrived quite rather late. But Edison was clever and jumped. He had no money as a boy, and he entered trains without permission as a pirate, so to say, and intercepted the telegraph, the railway telegraphy, and so we had an advantage, time advantage, about half a day or so, or one whole day, and he published his telegraphically received signals, informations as a private person by print, and this was his first money he got, and he contributed, yeah. And after Menlo Park was built and Edison invention as such, he was one of the first men to live from ongoing inventions in many fields, gramophony and movie. How shall I say? Because he invented invention, he invented the the idea of an electrical infrastructure for whole countries. In Chicago, there were no, in Chicago office use, there had been no electric infrastructure for everybody in every house, on every street. And there should be now, thanks to Edison, and so cities as New York and other cities were in a literal sense electrified. They got electrical energy, telegraphic information, cables, and there had to be power stations to produce electricity, transform stations to transform high voltages into lower voltages, and Edison had to invent a standardized electrical switch, identical in every house, in every room. He had to invent standardized twists in the electrical bulb, in millions and billions of mass production, and this was, I think, a very important and dramatic contribution to urbanism and modernization. Let's say the modern night is without stars, was with Edison's lamps and bulbs. At the end of his life, he, sad to say, he was less happy, but engaged in a bitter fight between an Edison company and Westinghouse company. It was a central issue, which kind of electricity would be the standard of our future modern life. And Edison was for DC, pleaded for DC, and Westinghouse, with good reasons, decided for AC, for alternating current, and that's why worldwide there is circulating alternative current 110 volt in the USA, and the double of it, 220 to 230 in Europe, and I think the rest of the world. And Edison was not too nice a guy. In order to gain his battle with Westinghouse, proved one apparatus, one device, sought for a device to prove the advantages of DC. And this device should be the device for electrocution. DC kills better than AC was his thesis. I think he was mistaken. But this was his argument, his bloody argument, and nevertheless he lost the battle and the war. The last remark, and we are at our end. It's important to say what Edison did not invent. His famous gramophone and his famous kinematoscope were not electrified, or only in a minor aspect for filming and reproducing these small films. An electric bulb or lamp was certainly needed, but it was no integral part of the invention. Both inventions were mechanic and optochemic, and that was it. And only in the 20s or this afternoon, I will come back to the electrification of the media of the 19th century. Thanks for listening. just have to announce Tania Hron with voice and beamer on the Berlin electrical traffic for some 20-30 minutes, and then we'll come back to the history.
Oh, I hope this is interesting for you. It was supposed to bring some flash and some insight into the rather abstract history of electrics and electrification. So Berlin has been one of the places where public transportation became electrical transportation, and that's why we want to talk about Berlin. And it's deeply connected with Werner von Siemens, about whom you've already heard, because he was the one that invented generators and dynamo and built the telegraph system, the electric telegraph system in Germany and elsewhere too. So, talking about what should I continue? Yeah. Sie wissen nicht. Talking about public transportation, first of all, takes us to something that is not precisely connected with machines, it's horses. Or actually the first public transportation in Berlin was people carrying other people in the 17th century, and you could hire people to do that, but it didn't work out that well. But until 1833, people had done that. Then they tried to install the same thing they have in Vienna in 1739. Due to a king's permit, some people found a company for horse-drawn vehicles and a Fiaker-Gesellschaft. Maybe people that have been to Vienna know the Fiaker. That's this horse cab that drives around the city and is basically carrying tourists. So this they had installed in Berlin too, but it didn't work out very well since Berliners were rather poor and couldn't afford it. Only after the wars against Napoleon, the droshky, a horse-drawn vehicle too, was set in place in Berlin, and in 1814 there was the first permit for 33 of these carriages, and until 1825 from 1825 on there had been droshkis that went from specific directions to specific destinations, and also had a timetable. And within a few years, until 1827, Berlin had 100, and something like 40 years later, 1,000 horse-drawn vehicles, and it became, and the number was increasing more and more the more years passed. So in fact, it could be foreseen that the horse-drawn vehicles wouldn't solve the problem of public transportation, which was needed to bring, let's say, the workers from the more inner parts of the city to the big factories that were situated outside the cities, at ports, for example, or at fields that were big enough to build huge houses and place for factories. The first thing that comes in mind that has to do with the connection of industry and different cities and places is, of course, the railway. Why was the railway such a big achievement? Well, you can transport much more goods and people, and society becomes mobile. And as Marx has once said, I can only rephrase it here, railroads were the thing that carried the regime ancien, so the old regime, to the graveyard, more or less. Yeah, the railway made the connection that made it possible to transport a lot of people. The first railway in Berlin was installed in 1838, so later than in England or elsewhere, and it connected the cities of Potsdam, Steglitz, Zehlendorf, all now, except for Potsdam, only parts of Berlin, but they had been communities or villages or small towns until the 20s of last century. And different railway societies built the railroads to Berlin, which hence, because of that, the many different stations, the Bahnhöfe, that are now subway or train stations, they were the ends of a specific train line, and usually they were the final destination, and usually there was no connection between the different stations. So imagine some train comes from the east, and it carries, I don't know what, sheep wool, and it ends at the Ostbahnhof, the eastern main station, but it has to be carried over to the west. So then some people had to take the wool out of the train, had to put it on a horse cab. The horse cab had to go from one train station to the other train station on the other side of the city. Yeah, that made the whole thing a little complicated. What is this? Okay, I think it's not that easy. And seeing this problem, a connection between all those trains was planned, and nowadays it exists, and it's called the Ring. People that have been to Berlin know this, S-Bahn Ring. This was to connect all these different train stations. It was planned from 1851 and replanned 66, and then finally it was built between 1871 and 1877. And as early as 1896, 103 million passengers per year were transported through the Ring. The next step was to connect all those stations through the middle, and they had built train tracks to do that, but still all these trains were running on steam engines, and that caused major problems for environment, noise of course. People that lived around the train stations and the train tracks were really annoyed by the noise and by the danger that was imposed by, of course, it was burning coal, so fire was always a big danger. And also the problem of the dust and clouds that were produced by steam engines couldn't be solved. So as soon as electricity was available, people were thinking about how can we try to get public transportation into being electrified. And the first step that was made to do this was done in 1881, I think. Let's see, by Werner von Siemens. Here he is. There has been a tram beforehand that was carried by horses, so the tracks were already there, or many tracks. Since 1852, there had been horse-drawn trains that ran on metal tracks or steel tracks, and they were first built in Paris and then in England and came to Berlin in 1865 because it was very expensive to build such tracks. Big companies had to, and consortia had to be found to actually make it possible to gather all the money to build these lines. But since Berlin became the capital of the Deutsche Kaiserreich, the German Empire, in 1871, it was in desperate need to provide public transportations that could carry more people than the normal horse cab. Because if you have a carriage on tracks, you can transport a lot more people by the same amount of horsepower. And just to annoy you some numbers, how much is it here? In 1895, Berlin had 55 horse trams that transported on a distance of 364 kilometers, 164 million passengers per year, so quite a huge amount. And also the several smaller communities that were surrounding what's now city center of Berlin built their own tram tracks and found their own tram companies, and often enough also had their own different size for trains and tracks and all this. So in the end, there were a lot of tracks already laid through the whole city, and this could be used for the electrical train. The first one was operating from the 16th of May in 1881, and it was actually an experiment done by Siemens. And well, as you see, he has developed many different electrical machines. This one, for example, being the dynamo machine from 1866, a generator. This is actually the technical means you need to have a motor. Here we can see the first electric locomotive that Werner von Siemens had built for the Paris Exposition Internationale d'Électricité. And as you can see, it's rather tiny, but it can carry a lot of people, and it indeed, within the time, when was that? Oh yeah. Oh no, this is not the Paris one. Sorry, this is the one in Berlin, and it transported 90,000 passengers within 4 months. It was also for an exhibition, and the one in Paris ran for this time of exhibition too, from Place de la Concorde to Palais d'Industrie, so only 500 meters. But that was the very beginning of trams. And here you see the engine itself. Yeah, it does not look like means for public transportation. It has this nice little chair for people to sit on it. It wasn't very fast, I have to say. It had a maximum speed of I think something like 15 kilometers per hour, and with people sitting on it, it usually went with 7 kilometers per hour. So walking might be faster. It's a little bit like these electric cars here in the village, I think. That's what you can compare it with. So becoming a successful company, Siemens and Heiske, that is their logo. The same company that also built the telegraphs, as you see, Telegraphy, Bauanstalt. They were the ones that got most of the public, was heißt denn Aufträge? Public permits for building trams. After the first tram in Berlin-Lichterfelde, that's this one, operated, they built more. This one here only connected one of the train stations, the from the Anhalterbahn in Groß-Lichterfelde, and a thing called Hauptkadettenanstalt. I think you can translate it into cadet school. So actually it was for military. Yeah?
West Point, so to say.
Yeah, okay, maybe West Point then. And it was this very little train went with electric energy using a generator, and it covered a distance of 2.45 kilometers, and it went on 180 volt co-flow, continuous current. So that was the beginning, and later this has been changed. And as you see here, there are no cables above. In the beginning, Siemens was using, the power he was using came from the tracks, from a little thing that ran inside the tracks, but it seemed this thing wasn't very practical. Whenever there was bad weather or snow covering this thing, the electricity didn't work anymore. So to make things more practical, Siemens developed cables that were above the surface. It's called pantographs. That's what I looked up in the dictionary. I hope it's the right term. And until nowadays in Berlin, these ones are used. Siemens also built the first trolleybus in 1882. Unfortunately, this was never very popular in Berlin, but it served as a role model for trolleybuses in England and in the States. He called his first trolleybus electromotive, and it covered a distance of 540 meters, so not very far, but it worked, and all these little engines were actually experiments to gather more knowledge to build bigger trams and to actually try out to electrify the whole tram system. And indeed they did this, and as early as in 1902 the electrification of the trams in Berlin was finished. On the 21st of August the companies held a farewell with all the horses, and from one day to the other there were no more horse trams running, and until that year only the biggest company of the horse trams had more than 6,000 horses. I couldn't find that, but I wonder what they did with all the horses after they had their trams electrified. Let's hope they didn't end as dog food, but probably they did, I'm afraid so. And yeah, the advantages of the electrification of the tram lines operating was of course that you could transport a lot more people, and indeed that happened. The number was increasing from something like 160 million to 623 million within a short time. And since this was working so well, other means of public transportation were also electrified. First, the metro. The metro is not a Berlin invention. The first metro was operating in London, and then in Glasgow, and then in Paris, but also with assistance of technical assistance of Siemens. And the first one in Berlin was built in 1886, and it was, funnily enough, not built underground but above ground, and that had to do with the sewerage system of Berlin. Like two reasons. One was that the ground level of the water is rather high in Berlin, so if you dig a hole, you'll find water, and so that makes the construction of tunnels a bit complicated. And the other reason was that Berlin had, for the end of the 19th century, I think the most modern sewerage system of Europe, which was built by Virchow, or a plant, and asked for by Rudolf Virchow, who is a victim of the electrification. Maybe that can be interesting for Friedrich Kittler. He used an electric tram, but he wasn't used to electric trams. They were faster than the horse trams. And the horse trams could stop everywhere you wanted them to stop. They didn't have like fixed stations. You just said like, stop, I want to go off, and you did. And they were slow enough just to jump off and jump on. Electric trams were faster, but Virchow, and being an 80-year-old man, was used to the horses, and he just jumped off. He fell down and he broke his leg, and he died after this broken leg didn't want to heal. Oberschenkel-Halsbruch. Yeah, precisely that. And he was actually also one of the big enemies against the Berlin subway. But the first one was built here, as we can see. It's nowadays the U1, that's why it's called U1, mainly above ground, and it has changed the track a little bit, but it's still basically operating the same way. And Siemens and Halske tested the trains for it, and then finally also provided the electricity because they had developed decentralized power stations and relay stations that could provide electricity. So in other words, they became like immensely rich, helping to electrify the whole city. And yeah, to cut a long story short, of course the First World War had some impact on the whole electrification project, and things were stopped to some point, but in the Weimar Republic in the 1920s happened what we nowadays actually call the great electrification. So everything that could possibly run on electric energy was electrified. The trains that beforehand were operating with steam engines were turned into electric trains. The U-Bahn was built, many different lines, new tram lines were built, and everything was electric. And yeah, I think back then Berlin must have been a really interesting place. And Siemens, who had started with a small wheel building factory with the telegraphs, within 3 decades became one of the world's largest companies for everything that had to do with electricity. They started to, and one could say,
About a quarter of Berlin, Siemens Stadt.
Yeah, they they started with the telegraph, then they moved on to public transportation. They have invented machines that were using electricity. I mean, there was no washing machine before that, and there were a lot of tools and machines that Siemens invented, then provided and also provided the energy for it, and built together with AEG also the big power stations in Berlin. They built their own quarter, the Siemensstadt, which is nowadays still existing, and they built the tram tracks for Siemensstadt and the stations. And they had also developed a whole new culture of companies. Like they had built factories, and on the site they built houses for the workers, and also architects were included in this. Maybe if you want to see some more images of the train, this, for example, is one of the first U-Bahn that was operating. This is the U2, I think. In 1908. And this is the ring that connected all the different stations. Some of the older Berliners still know it as the Hundekopf, the dog's head, because it looks like a dog head, doesn't it? Yeah. And yeah, that's a Paris tram, and it was also built by Siemens, I think. And the history of the Berlin transportation, public transportation stations is connected with two names only, more or less. Maybe architects only know them, Richard Brademann and Alfred Grenander. So the S-Bahn was basically, the S-Bahn buildings were basically designed by Richard Brademann, and the U-Bahn buildings by Alfred Grenander. But not only the buildings, but also the place that were hiding the relay stations and the power stations and all this. And you can still recognize that in Berlin, this very specific style. Like this is an example for a Brademann building, that's Gesundbrunnen. No, it's actually Bonner Straße. Interesting place, because this is where the wall opens in the night from the 9th to the 10th of November in 1989. Right there was the place where it first opened. Here is a subway station that was designed by Grenander, who started with an Art Deco style, but ended in, as you can see here as well, Wittenbergplatz, and ended in a much more modern design, like this, for example. And that here is the S-Bahn, underground, funnily enough, designed by Brademann in a very typical modern way. And yeah, I think that's all I have to say, unless you don't